हेलो बच्चों, सत श्री अकाल एंड नमस्ते from my side. Okay, so this is your own physics educator Indrajit Singh, right? Again, welcoming to the chapter of dual nature of radiation and matter. So as usual, I think it's important to understand that the ray optics is a giant. Once if you are able to understand in the 12th syllabus I'm talking about, the electrostatics is the fundamental part. Then magnetism it's a bit boring. There comes the giant, that is the ray optics, and after that things are going to be quite easy, right? So the same reverse engineering we are going to follow because we have to cover up the entire chapter into the minimum time. So first of all, we are going to see the PYQs, and through PYQs we are going to watch this, right? The sums and the concepts and everything, right? So without wasting our time, let's move on, right? Okay, the agendas of today's session will be the practice question. Through the practice questions we are going to see, okay, the sums based on it. Okay, so let's continue. So as I told you all into the previous lectures, right, the most important thing of the dual radiation and matter we are going to cover up into the one lecture. Basically, first we will have the simulation, then we'll have an explanation, and slowly we are going to move forward for the sums. Okay, so I have summed up, okay, the entire dual nature. After that the atom will come, and after that the nuclei will become. So for this 3 lectures, right, we have did something special. Okay, we are going to follow the reverse engineering. Reverse engineering itself states that we are going to pick up one question, and after that we are going to see theory from that. And if that question would be the PYQ, then it would be the awesome. It is going to be an awesome part of an preparation. We are going to see some PYQs, and through PYQs we are going to see all of those theories. I think that is going to be the great part. Okay, that is going to be the great part. Okay, yes or no? So are you all ready for that? Yes or no? Are you all ready for that? So here one thing is that, okay, I am going to, Einstein was awarded the Nobel Prize not for the equation he gave, not for the theory, right, that changed the scenario of the science. And okay, I'm sorry, okay, he was not awarded for the theory, okay, that changed the scenario, okay, that changed the point of view for all of those scientists, but he was rewarded for the photoelectric effect. He was not rewarded for the theory of relativity, okay, from which the concept of the black holes and blah blah blah, blah lots of things has arrived. But for solving the problem of the photoelectric effect, right, he was awarded for the Nobel Prize. That was again a great thought, is a food of thought for all of those scientists at that time, but it happened. So what does this photoelectric effect means? That first of all we are going to take one simulation, and then we are going to move on slowly onto that. Okay, in this simulation we are having one source of light. Okay, this source of light gets incident on specific surface, and that surface emits the electron. You want to see into the simulation? Let's check it out. Right now I am using the wavelength of light, okay, is 400 nanometer. 400 nanometer. Right now I kept the intensity as 0 into the simulation because we want to we are about to start it. Okay, now what will happen? Suppose if I am increasing the intensity, the light gets incident on this surface. See, something is something is coming out from that surface. the two surfaces, the one side is connected to the cathode of the battery, the second side is connected to the anode of the battery. Okay. Again, I am taking the intensity as 0. The phenomena, the activity that went on, it got stopped. The phenomena, the activity that went on, it got stopped. See, now I am going to increase the intensity at the maximum value. Something evolved from this plate. Can I consider this is a cathode? Can I consider this is an anode? From cathode to anode, something is getting evolved. What are those particles? How are you going to name that? Okay. Initially, those were at rest. Now they are moving with some specific speed. So they might be having some kinetic energy. Okay. Lots of thoughts we are having. We are the observer. We are going to analyze this activity. Lots of things are happening in front and we have to represent all of those stuff into the mathematical form with the appropriate logic behind it. Physics is having the kind of a flow. First, the logic is developed and then slowly theories are defined and then the mathematical representation is given. So same thing, we have seen an activity. We are going to define some things. We are having some noticeable observations. Okay. Now suppose if I want to reach up to the accurate results, okay, then I have to tickle up into an experiment. Okay. Suppose if I am changing the wavelength of light, something happens? No. The light is at the maximum intensity, still it is getting incident on the specific surface. When I was using the light of the wavelength 400 nanometer approximately, right, the particles were emitted, the particles were getting out from that specific surface. But when I changed the wavelength of the light, right, to some value, okay, the activity that was going on, it got suddenly stopped. Somewhere wavelength is involved into the phenomena very hardly. Because by changing the wavelength, the observation that we have seen before, the emitting of the particle from the specific surface has got suddenly stopped. It means that wavelength is having the appropriate role within it. The wavelength is having the appropriate role within it. Suppose I am changing. This surface was previously of sodium. Now I changed it to zinc. Again I am going to take back as something, okay, some of the particles are getting out from that specific surface. Now let's change wavelength of the light. Again back to the 400, nearby 400. Boom. Into the previous case, when this surface was made up of a sodium, particles were getting completely out from that specific surface. Even, alright, the light that was getting incident on the surface was having the wavelength of the 400 nanometer. The particles were getting emitted. But in this case, when the nature of the plate, the metal, the material of the plate was changed to zinc, and on the same value of the wavelength 400 nearby to that, nothing is, no observations are there, huh? No particles are getting emitted. Suppose if I am getting changing the wavelength, is it possible? No activity. Yes. Boom. So it means that two most important things are involved here. The first, the wavelength of the light that is used to incident, right? The wavelength of the light that is getting incident on this specific surface. And second important thing, that is nature of the material that is used into this arrangement. The nature of the material that is used into the survey. Now, suppose it is connected to the battery. Again, you can just check it out in this simulation. We are going to get, we are having the value of the current. as because of the surface is emitting the particles are moving from cathode to anode. Okay, those are nothing else but the photoelectrons. But how we are going to prove that? Slowly we are going to see up into the theory, right? So those particles that are getting emitted from this specific surface, right, gives the rise of the current into the circuit as 0.8 ampere. It means that somewhere current is involved. Wavelength of the light, nature of the material, and current. The three most important factors we have reached up to the, right, we have reached onto the three most important factors that are completely involved in this kind of the phenomena, right, in this kind of the phenomena. You can just check it out in all of those three graphs. This is a current versus battery. Battery supply is 0, but still there is a current into the circuit. You can just check it out. See, battery supply is 0, still we are having the current into the circuit. Current versus light intensity. Slope is a straight line, right? Energy versus light, this is we are going to see afterwards. See, now I'm going to change the value. Okay, the motion of the charged particles got changed. Previously they were into the high motion. See, now slowly moving. It means that somewhere with the light intensity, the motion of the electrons or the motion of the charged particles, those are getting emitted out, right? They are also related. Okay, so it means somewhere in this theory, intensity, right, the energy that this particle possesses, the nature of the material of the surface, and the value of the current, these four factors are somewhere involved, right? So this phenomena, it is nothing else but the photoelectric effect. Okay, the emission of a particle from this specific surface, that is photoelectric surface, you can say the photosensitive surface, right, give the rise to the current into the circuit. The effect that has been noticed in this kind of an arrangement, it is nothing else but the photoelectric effect. And we are going to analyze this and the PYQs based on that from the dual nature of, okay, in the dual nature of radiation matter. Apart from this, right, some of the important theories like Bohr's equation, not Bohr's equation, sorry, that de Broglie wavelength for the charged particles and everything is there, and some of the radiation pressure and force direct formula based questions are there. Okay, so this would be the most important part, and we are going to directly focus on that. Here, the most important thing that we are going to study, that is a photoelectric effect. Okay, we have seen into the simulation. Okay, we have seen this effect into the simulation, but now I'm going to give you all the detailed explanation of it, the exact terminology that is given into the resources of the books. Okay, see, for this photoelectric effect, we need one kind of a specific arrangement. Okay, specific arrangement states that we need a source of light that is having the capability to produce, or that is having the capability to emit, right, the what we can say, the n number of the wavelengths whatsoever we desire to. Okay, now for this I'm going to take two plates. This is a first plate. This plate, it is also known as a photosensitive. In some of the cases, it is also known as cathode. Why it is cathode? Because those two of the plates are connected to the battery. This side I am taking the another plate. Okay, the first plate is connected, right, to the positive terminal of the battery, and the second plate is connected to the negative terminal of the battery. And why this battery is used? Okay, this is a suspense and it will be revealed. Like generally this happens into the horror picture. Now the things get revealed at the end. The same thing we are going to see right at the end. Why battery is used? What is the purpose? Sir, if the light is getting incident on the specific surface, please don't mind, right? We are getting the photoelectrons, and what is the use of the battery? We are getting the supply. We are getting the photoelectrons, and for that we are having the value of the current. Then why there is a use of the battery? Unnecessary, sir. You are from where this kind of sir comes. Okay, one day we are going to use that kind of the English, really. Okay, from where this kind of sir comes. No battery use, but still battery keep what? Physics, what? Source of light use, okay. Two plate use, okay. Why battery? Many students might be to the cursor, what kind of English it is this? One day definitely I'm going to conduct this lecture in the same way, and you're going to enjoy each and every moment of it. I guarantee. The motive of the lecture will also be followed, right? You will understand all of those concepts also, but the language would be different because that is indeed needed. Okay, so now let's come back to the arrangement. Okay, sorry for that time. Okay, so this is a photosensitive plate. As usual, we decided, we saw into the simulation, right? The nature of the plate matters. How nature of plate matters, we are going to understand. Okay. See now what happens here. Suppose, okay, the wavelength of the light, lambda, okay, is getting emitted from the source and gets incident on this specific surface. Okay. A wavelength, a light of the wavelength, the specific wavelength is getting incident on the specific surface. Okay, and suddenly from this photosensitive surface, right, electrons start moving on from this point, right, to this. Okay, those emitted electrons are nothing else but the photoelectrons. The emitted electrons, right, from surface, they are nothing else but the photoelectrons. They are nothing else but the photoelectrons. Yes or no? Okay, they are nothing else but the photoelectrons. Now what happens here? Okay, what happens here? Okay, suppose if I am changing the wavelength of the light from lambda to 2 lambda, right, is there any change of the motion of the electrons? Yes, there is possibility that it might be possible. If I am changing the nature, of the surface, changing the nature of the surface, is there any kind of the change into the motion of the emitted electrons? Yes, there is a possibility. So here how we are going to represent this mathematical system? Suppose if I am replacing the value of lambda to lambda by 29, is there any kind of a possibility that electrons may get emitted? Or there might be some specific value of the lambda, na? There might be some specific threshold value of the lambda beyond which all the time the electrons will emit. Below the value of that lambda, no electrons will emit. So there is a possibility. So first of all, I want to represent this equation, the photoelectric equation, the correct mathematical representation of this photoelectric equation. Okay. See, first point. Light gets incident on the photosensitive surface. Lights get incident on photosensitive surface. Yes or no? The light gets incident on the photosensitive surface. Second, the nature of surface will decide the emission of the electrons. Depending on the nature of the surface and the incident light. Depending on the, right, okay, two most important definition we are going to see, that is the work function, right, work function of the metal, and the threshold frequency of the light or threshold wavelength. Okay, the terminologies into the photoelectric effect are quite nearer and students always used to get confused within it. Okay, so the light gets incident onto it. Okay, suppose it is crossing the threshold value and the electrons are getting emitted, and when the electrons are moving on from the cathode to anode, they gain some kind of energy which is known as kinetic energy. Right, so it means, can I say that the energy that is incident, that is getting incident on the photoelectric surface, is hc by lambda from the source. If the light is getting incident on the photosensitive surface, okay, there might be some property of this photosensitive surface. I told you all, there is a property, there is a threshold value for this photosensitive surface beyond which, okay, the electrons will definitely get emitted. So here comes the definition of work function. The minimum energy needed for a photosensitive surface to emit an electron the minimum energy needed for a photoelectric, see, here it is a surface. If the light is getting incident, let us take an example, it is 10 electron volt. Okay, but the metal needs 12 electron volt minimum to emit an electron. So is it 10 electron volt that has been given to the from the source? Is it enough to emit an electron? No. Why? Surface is having the capability, right? I want 12 electron volt and then I will emit an electron. So he says increase. Now this work function of the metal, it is a minimum energy needed from the source, right, to emit in photoelectrons. But in this case, it completely depends on the nature of the metal. We have seen into the simulation, first we took a sodium and then we changed it to the zinc. Okay, so depending on this nature of the metal, this work function is decided. Suppose there is a possibility, if I am using another photosensitive surface, right, that is having the photoelectric, that is having the work function of the 6 electron volt. So it means that if the source is going to give the 10 electron volt, okay, the 6 electron volt is the work function. After that, electrons will get emitted. So the same thing, see, source is same, but we are having the two different cases. In first case, the work function of the photosensitive surface is 6 electron volt, okay, in which the electrons are getting emitted. But into the second case, the work function is 12 electron volts, but in that case, the electrons are not getting emitted. This is the thing. Okay, this is the thing that we have to discuss. Okay. So it means that one thing is for sure, whatever it is going to incident on this photosensitive surface, okay, some part will get confused, like will get consumed into the work function. And whatsoever the energy that is remaining, it will be given to an electron and they will have a motion from cathode to anode. So it means here one thing is fixed, that if energy is less than work function, then no emission of electron. Energy should be greater than work function. Then and then there is a possibility of, right, electron emission. The most important points we are about to note it here. Okay, 6. So it means that one thing is for sure, the amount of the energy that is incident minus work function, okay, this is equivalent to the energy given to electron to move from cathode to anode, right? This is an energy given to an electron to move on from the cathode to anode. So it means that energy incident minus work function, that is equivalent to kinetic energy of an emitted electron. It is for sure na yaar. See, simple, it is very simple thing. Work function is 6 electron volt. We are giving 10 electron volt. 10 electron volt given, work function consumed 6 electron volt, right? Remaining the electron will emit, the emitted electron will have the kinetic energy of the 4 electron volt. That's it, a very simple calculation. This is an actual mathematical representation of the photoelectric effect. The actual mathematical representation of the photoelectric effect. Okay. Incident energy minus work function, that is going to give the kinetic energy of the emitted electron, or in another sense minus, right, half mve square. This is the actual, generally in many of the resources it is given the energy emitted, it is equal to work function plus kinetic energy. I must say, okay, they have rearranged the terms, but it is logically incorrect. The difference of the incident energy and the work energy, work function, okay, it is only the amount the electrons will get to emit from the photosensitive surface. The electrons will get to emit from the photosensitive surface, right? So from now onwards, whenever we are seeing this, right, okay, for the photo, this equation, it is nothing else but the photoelectric equation, right? This equation is nothing else but the photoelectric equation. So it is phi plus kinetic energy, it is E minus phi. This is the correct equation, and this is nothing else but the photoelectric equation. Now in this, the two terminologies we are going to see, the first one, that is the threshold frequency and the stopping potential. This side we are going to see the stopping potential. Okay, the both are correlated to each other, right? Okay, and the threshold frequency. Now what is a threshold frequency? The threshold frequency is associated with the work function. Minimum frequency needed from source, right, on plate to emit an electron. Minimum frequency needed, right? Threshold frequency is a minimum frequency needed from a source, right? Minimum frequency needed from a source on the photosensitive plate to emit an electron. Suppose if the source is giving 6 electron volt and the work function is a 6 electron volt, right? So everything will get consumed. So here can I say the work function, that is equal to HF0, where F0 is the threshold frequency. F0 is what? Threshold frequency. Now what is the stopping potential? Okay, these are the terminologies you always used to get confused. Work function of the metal, the energy incident, the kinetic energy of the electrons, and the stopping potential. See, now everything is going on, the electrons are getting continuously emitted from the photosensitive surface. Okay, now we want to stop the motion of the electron. We want to stop the motion of an electron. To stop the motion of an electron, see, the electrons that are emitted from the photosensitive surface, right? So they gain some kinetic energy. This thing we have discussed, na? Kinetic energy is equal to E minus phi. The work function, energy incident minus work function. So it means once they are emitted, they are having the kinetic energy. Once electron are emitted, they have kinetic energy. To stop them, we have to do work. Now, how we are going to do the work? Negative potential is applied from the battery that will work against the kinetic energy of the electron and will stop them. Negative potential is applied from battery. Now, how you are going to decide how much negative potential should be applied? It completely depends on the kinetic energy. The amount of the kinetic energy electron possesses, same with the negative value, is applied from the battery from anode. So they will contradict each other and the motion of the electron will get resisted, and finally after some amount of the time it will get stopped. So stopping potential, I can say kinetic energy, that is nothing else but equivalent to half mv0 square, that is in electron volts. Right. So there is the difference into the photoelectric effect. Threshold frequency is something else, stopping potential is something else, work function is something else, energy incident is something else, right, and kinetic energy is something else. Right. This is a correct equation. Within that, this is a threshold frequency, this is a stopping potential. So this is a correct representation of the right photoelectric effect. I'm moving aside on the countdown of 10 seconds. If you just note this down, you can. Okay, I think that much time is enough. Okay, if you want to see the light is used, for this reason the battery is used. Okay, the negative, this is a positive, sorry for that. To apply this stopping potential to the specific, right, to stop the motion of the electron, okay, now there are some graph based on it. Okay, the graph of photoelectric current versus variation. Okay, the saturation current and everything. I'm moving aside. You want to just have a screenshot for it, you can, because directly we are moving forward to the PYQs based on that. Right, directly we are going to move forward for the PYQs based on that. Okay, I think that much is enough. Let's move on to the sums based on it. As used per our tradition, I'm going to give you all a 1 minute to solve this stuff. Sodium and copper having the work functions. Now the terminologies are cleared, right? Before moving on to this sum, I want to tell you all if the difference between the terminology, work function, the stopping potential, the threshold frequency, the incident light and the kinetic energy, if it is not clear, please move on to, please rewind this video and watch it again. Okay, otherwise this sums will be like hell for you all. Sodium and the copper are having the work functions of 2.3 electron volt and 4.5 electron volt respectively. And the ratios of the wavelength will be nearly equivalent to what? A very awesome sum. But I want you all to immediately solve this. Come on. Okay, without wasting your time, we are going to see those sums and immediately jump off the conclusions. Yeah, it is not a matter of a minute, it is just a matter of the right seconds. In 4 to 5 seconds we can solve this. I'm going to shut off this AC. Okay. See what happens here. Practically speaking, what happens here. Okay, see work function. The work function is associated with the threshold frequency, right? So phi 1 that is equal to HF1, phi 2 that is equal to HF2. We need to calculate the right ratios of the wavelength. So can I write it as HC by lambda 1 that is equal to HC by lambda 2. Okay. Now see the work function of first and second. Can I say the ratio as phi 1 by phi 2 that is equal to lambda 2 by lambda 1. So here lambda 1 by lambda 2 ratio it is going to come upon as nearby equivalent to 2:1. Okay, 2:1. I told you all it is associated with the C is the perfect answer for this specific question. C is the perfect answer for this specific question. Let's move on to the next question. The formation of the covalent bond in a compound exhibits wave nature of the electron, particle nature, both wave and particle nature, none of this. Question is asked in EIEEE 2002. Okay, let's give you all a time. Okay. Come on everyone, it's just a matter of seconds, not a minute. Okay. See, formation of the covalent bond. The covalent bonds are formed by sharing of an electron, okay, to an opposite spins. This thing you have seen into the chemistry, and this can only explain the wave nature of an electron. Okay, this can be only explain wave nature of the electron, and first is a perfect answer for this specific question. This is the theoretical part that you all have seen into the chemistry. Okay, now let's move to the next question onto it. According to the Einstein photoelectric equation, the plot of the kinetic energy of the emitted photoelectrons from the metal versus the frequency of the incident radiation gives the straight line whose slope depends on. Okay, the question states the graph of kinetic energy versus incident radiation, right? Okay, incident radiation that is equal to hc by lambda. The graph of the kinetic energy versus incident radiation, it is a straight line. Okay, whose straight line slope depends on, nice, whose straight line slope depends on. Let's give you all a time. School question. If If I'm following the photoelectric equation, mark my words, then kinetic energy it is given as E minus work function of the metal. If the work function is 0, then this graph is possible. But is it possible in any case that work function may get 0? No. Okay. So the actual graph of the kinetic energy versus incident radiation is like this way, and this is nothing else but the work function. So if I am comparing this graph to the equation of y is equal to mx plus c, the value of m is slope, right? Value of the m is slope. So here slope is nothing else but the Planck's constant. It is independent of all. Slope is nothing else but the Planck's constant, right? I heartily apologize for my word, for incident. It is independent of the all parameters. Right? So here D is a misprinted option. It's not present. So D is the perfect answer for this specific question. The work function of the substance, it is given as, the work function of the substance is 4 electron volt. The longest wavelength of the light that can cause the photoelectric is approximately equivalent to, very simple question, right? The work function, that is nothing else but the 4 electron volt, right? Okay, work function is 4 electron volt. So the maximum wavelength of the light that can cause the photoelectron, it means we need to find the threshold frequency, threshold wavelength. See, for the V0, V is equal to lambda F0. This is the threshold wavelength. For this threshold wavelength, we are having the threshold frequency. Right? So the work function is associated with the threshold frequency, and for the specific threshold frequency, we are having the threshold wavelength. Right? So it's just a simple calculation. Come on, everyone. Okay. Come on, everyone. Just a simple calculation. We have seen this into the theoretical part. Let's not waste time on that, right? So this is lambda 0 is equal to 6.6 into 10 to the power minus 34 Planck's constant, 3 into 10 to the power 8, right? Lambda 0 is 4 electron volt. 1 electron volt is equal to 1.6 into 10 to the power minus 19 joule, right? So this lambda 0, it is going to come upon as 310 nanometer. Okay, C is the perfect answer for this specific question. A charge, or yeah, this is a a photo cell is illuminated by the small bright source that is 1 meter away. When the same source of light is placed at the half meter away, the number of the electrons emitted by the photocathode would be. This is a homework from my side, right? This is the homework from my side. Okay, you have to answer beneath the video. You have to answer this homework, right, beneath the video. Okay, the one question that I've given you all into the homework from my side, you have to answer beneath the video. I think that much is enough for the dual nature. Apart from this, okay, let's see this. The kinetic energy of a free electron doubles, then what will be the de Broglie wavelength? By what factor the de Broglie wavelength changes? There are some of the de Broglie wavelength equation. The first one, that is for hc by lambda. Second is for the accelerated charged particles with some potential. Okay, some 3 to 4 equations are there that is directly mentioned into the books. Okay, one question is asked from this. We are going to see that, but before that, let's give you all a time to solve. The de Broglie wavelength equation is represented as E is equal to hc by lambda. Okay. Sorry, this is an energy equation, right? Lambda is equal to h by mv. This is a de Broglie wavelength. I heartily apologize for that. Can I say lambda that is equal to h by momentum? Momentum is nothing else but, right, under root of 2m kinetic energy. 2m kinetic energy, right? So this is nothing else but the de Broglie equation for the charged particles, right? De Broglie equation for the accelerated particles. Okay. So comparing this, you are going to have lambda 1 by lambda 2, that is equal to under root of k2 by under root of k1. So lambda 1, right, by lambda 2, it is going to be approximately kinetic energy is getting doubled, huh? So it is root 2 by 1. Okay, so lambda 2 that is equal to lambda 1 by root 2. So it changes by 1 by root 2 factor. The B is the perfect answer for this specific question. So students, it was all about the dual nature of the radiation and matter. Thanks a lot for your time and cooperation. I think it's time to go. Again, we'll come back into the next chapter, right? So this is your own physics educator Indrajit Singh signing off from the desk. Bye bye. Sat Sri Akal and Namaste from my side. Bye everyone. Stay at home, stay safe, stay healthy amidst this pandemic and take care. Bye.